What's up, guys? Chris from Green Bench here. So on Module 4, we're going to start wort boiling, discuss sort of characteristics and what we get, why we boil wort. Let's hop right into it. So there's a bunch of things here. These are the basic reasons in which we boil wort. So there's sterilization that we're going to discuss, hop isomerization, terminate enzymatic conversion of the wort, coagulation of proteins. We remove volatile compounds. We concentrate the wort volume. We concentrate the wort color. There is wort acidification that's important. Creating formation-reducing compounds, which we'll discuss. And a required reading, we have a couple good ones. These are some of my favorite ones, actually. In the link here, we'll have the title of the paper, or the page that was written is called Wort Boiling Today. And there's also the function of wort boiling, which the link is there as well. And the wort boiling today, just pages 1 and 2 of that one. If you want to read more, by all means, it's fairly fascinating. So here we go. So sterilization, let's start there. So raw materials contain microflora, plenty of them, lots of microorganisms, lots of bacterial strains. A common one would be, for example, lactobacillus is commonly found on the outside hulls of grain. So boiling neutralizes the living microbes present in the wort. We make wort, there's a ton of germs in there, not germs really, but there's microorganisms, there's bacterial strains, wild yeast, all sorts of stuff. Boiling kills all those. So that's what's important about sterilization. Hop isomerization. Isomerized hop acids result in perceived bitterness. The longer boiling times for hops increase the isomerization yields. Higher pH increases isomerization yield. We talked a lot about this in the last slides, that the longer you boil a hop, the more bitterness you're going to extract from it. This is because you increase the yield of your isomerization. The higher the pH, meaning the less acidic something is, the more base that it is, increases the isomerization yield. We mentioned this too in the last slide, where if you have an acidic wort, or if you decrease the pH, you actually can decrease the amount of bitterness that you get from hops because you're decreasing the isomerization yield. So a higher pH is going to increase that, a lower pH is going to decrease that. Terminating enzymatic conversion. So when we're boiling, we're actually stopping the active enzymes from the mash tun. So for example, when we mash, what we're doing is through hydrolysis, we're converting starches, carbohydrates into simple sugars, as you definitely learned in a previous module. This is through enzymatic conversion. So for example, remember your alpha and your beta enzymes that are converting simple sugars, dextrose, and complex sugars, dextrins, more complex chain molecules. This still happens. So when you louder to the kettle, there's still some conversion happening, which is why, for the most part, when you're sparging, you're going to want your temperature at 168 to 172, 170, kind of be in that medium Fahrenheit, because this, for the most part, neutralizes enzymatic conversion. It doesn't exactly happen 100%. It slows it down and stops it, which is required. When you boil it, you definitely stop this from happening completely. The problem is that if you continue to enzymatically convert, it says here, extended enzymatic conversion will result in altered fermentability. So for example, if you're fermenting at 152 degrees Fahrenheit, or even lower sometimes. So if you go in high, for example, and then you transfer to the kettle, sometimes if you don't stop the enzymatic conversion, you can convert some more simple sugars than you wanted, resulting in your beer drying out. Or the opposite, you mash in very low, you transfer to the kettle. It's essentially a step. Some of those sugars or the carbohydrates that hadn't completely converted yet, because of the increased temperature, will then turn into a very complex chain, which can hinder how dry your beer gets, because you want it to be. It can be a little bit sweeter and maybe not attenuate as far as you'd like. All right, so coagulation of proteins. Boiling produces proteins and polyphenols that both precipitate as hot break and cold break. Precipitation and removal of coagulation helps promote healthy fermentation and higher stability of the finished product. So, for example, coagulation needs to sort of be separated. It needs to be taken out. You have to coagulate in order to separate the proteins that are in suspension. Too many of these things, coagulation can compromise the yeast cell walls. You have too much protein in there. That's why when you do a whirlpool, that's why people add Whirlfloc and Irish moss, like I mentioned in the last slide, which coagulate these proteins, force them out of suspension, and then fall to the bottom and separate the liquid from them. Coagulation, like I said, can compromise the yeast cells. themselves can compromise the walls. Coagulation can cause a very harsh, sort of weird, acrid, undesired, harsh bitterness. It can also hinder colloidal stability, and it can negatively affect the clarity. And I thought I guess I'm pretty good. I'm just barely covering the last S there on bitterness. But so it can affect all those things. This is why coagulation is extremely important. And when you boil, some brew houses, some kettles, frankly, will be able to coagulate proteins very efficiently just in the boil. For example, ours, we actually recently stopped using Wort. Not to say you should do that by any means. Most breweries do it. We started using it. But I found that we were coagulating so well with our water profile and the efficiency of our boil that everything's just sort of fell out of suspension anyway. All right, so the removal of volatile compounds. When you boil something, obviously you have evaporate, right? What happens in the wort boiling is that oftentimes what you'll evaporate contains a lot of unwanted volatiles that come from the malt, the hops, and the boil itself. So, for example, the most common would be DMS, which is dimethyl sulfide, which often is an off flavor that is from the malting process. So it's in everything. Like DMS is in every single beer, but it's threshold levels that matter. You want to get rid of as much as you can. So extended boils can often get rid of this. It comes across as corn-like. Sometimes it can actually also be green olive can be the characteristic you can get from it. However, it can easily be avoided with increased boil or rapid boils or aggressive boils. It evaporates right off. All right, concentrating of the wort volume. So wort boiling evaporates water, including the volatiles. Breweries usually evaporate between like 8 and 12% of the initial wort volume. So you'll lose volume essentially post boil because you're evaporating off some of that volume in the wort, which again concentrates the wort volume, gets you to where you need to be as far as your full volume. It also concentrates the wort color, and because it concentrates the wort volume and the color, what you're usually boiling off in the wort. Actually, we'll go back real quick. What boils off in the wort volume is usually water. So what you're left with is a concentration of sugars. So your gravity should be higher, usually about a good point higher between pre-boil gravity and your post-boil gravity, because you're boiling off water, you're concentrating that liquid. Now what you have left is sort of a more concentrated sugar water, or the wort. Sorry, now we're going to go to wort color. We'll talk a little bit about a Maillard reaction. So Maillard reaction is a reaction between amino acids and reducing sugars, resulting in melanoidins. Melanoidins is often called browning. Browning is essentially a caramelizing of the sugar, caramelization of the sugar, which literally turns the beer kind of brown. Melanoidins also taste very bready. So there's actually melanoid malt that has gone through this process for you as a modification. Gives you this really cool brown, red color, and tastes softly bread-like characteristics. So, but when you concentrate the wort by boiling it, all the wort kind of goes through this process where there's this reaction through this amino acid and these reducing sugars that result in sort of this browning process. Sort of increases your color. You can also, especially in direct fire systems, have that scorching characteristic, which will caramelize the sugars and give you this as well. So you have an increased Maillard reaction, or more of it rather, in sort of kettle design, based upon, like, for example, direct fire systems will have this more often than others. Wort acidification. All right, so boiling acidifies the wort, usually about 2 pH per hour. So for every hour that you boil, you'll see a drop in pH of about 0.2. Now this comes from a lot of things, not just like from the actual boil itself. So your water hardness, your hop acids, melanoidins, all those things will affect that. And so the longer you boil, the more of those you get, the more hops you isomerize, the more melanoidins you'll get from the scorching, and depending on what the hardness of your water is, your calcium, magnesium, which interacts with the phosphates in the solution, will decrease your pH a little bit by acidifying it. Now, here's something else too. Darker wort drops pH a lot farther. So you have your Maillard reaction here, right, which is your melanoidins that are being created. the darker the grain, just in the process of before it even got to you, in the process of modification, the process of roasting. For example, if you take a grain, a 2-row base grain, and you roast it to a caramel 80 specification, it is more acidic than, for example, just the base 2-row is, because you have caramelized it. You've created the melanoidins just in the process of roasting it and caramelizing the sugars that, because of the moisture involved in the roast, actually some enzymatic conversion happens inside of those kernels, creating sugars that are then caramelized with the heat, creating a darker color, which your pH is also going to drop because of that. All right, formation of reducing compounds. So, reducing compounds aids in delaying oxidation and spoiling in finished products. For example, things like melanoids, or melanoidins, they actually assist in keeping oxidation and spoiling out of beers. So, which is oftentimes, I mean, not completely, but oftentimes why sometimes darker beers can last a lot longer as far as spoilage goes than lighter beers. In addition to that, sometimes what you'll see in packaged products that are, for example, mostly oxidized, will actually create melanoids and browning and have to go through a Maillard reaction just because in the presence of oxygen itself, there's amino acids that are reacting in the final products. The other thing, last thing, are the other reducing compound would be reductones, which essentially are caramel products that act like antioxidants. So the higher the sort of caramel characteristic, the higher the sort of roast levels in the grains, the better suited that beer, frankly, the product is, to delay spoiling and oxidation of the final product. So that's it for these slides, and we'll see you in the next one. Thanks, guys.